Potential energy of a thin wooden rod hanging partially in water. What is the wood density in the state of equilibrium? First, let me introduce some constants. So rho W and rho naught are wood and water densities. Usually, the density of water is the standard for different densities. So if something is stickier than water, then you would say it has higher density, and vice versa. But that's just some physics talk, I guess. And now you have the volume and length of the rod, the wooden rod we're talking about. G is your very famous 9.80 something gravitational constant. Nothing too special. H is a constant which fixes one of the rod ends, and phi is the only variable that's actually a variable and that changes. And in this case, because it's in the cosine, then probably it's an angle at which the rod is in water. I'm guessing, of course. I'm no physicist, so I have no grasp whatsoever of the whatever meaning is behind this problem. That's good. So phi is changing, and with it changes the potential energy. Then probably I can say that the potential energy is a function of phi. And I can verify this just by reading the problem statement, which I've not written all of here. But we are told that the equilibrium position can indeed be found by minimizing the potential energy, or by finding the phi, which minimizes the potential energy. So at least we have a goal now, which is to find the to minimize this potential. As with any optimization problem, you have a function, you take the derivative, you set it to be equal to 0. So this should be standard now for you. But for me, before I take the derivative, I would just like to do some brief manipulations, just for the sake of niceness. Maybe it's a good word. So I've separated now the part with the variable from the constants. And I'll do this once again. Here this is a constant, and here we have a division by 2. It's also a constant. And then what? Then there's this squaring and there's cosine of phi. So I would like to expand this, but that is just a preference of mine. You don't need to do like me. With mathematics, you can reach a solution in a multitude of ways. It doesn't have to be my way, but this is how I would do it. So if I want to expand this, I would get 1 squared minus 2 times h over L times 1 over cosine of phi. And then I would square the second term, so I would get h squared over L squared times cosine of phi. Then I would just remove the power, and I still need to distribute this guy. This is in the denominator. I'm glad I was able to see this, otherwise I think I would have had to re-record this, which is not so pleasant. Here, I'll write the same expression, but the difference is that I will be distributing this quantity on the 3 terms that I have. So very briefly, it's not difficult to see that the first term will be cosine of phi. Second term has cosine of phi, so probably they'll cancel out. And as for the final term, which I have written incorrectly again, but since I've seen it, I don't need to redo the video once again. Again, the mistake is I should square all the terms, so I did not square the cosine. Anyway, now that we're here, I still need to multiply this by cosine, so the power will go away and then you will get phi. Then maybe I had this in mind all along and it wasn't a mistake, you know. Whatever that means. But I think for me, from my side personally, I think I'm ready to take the derivative. So I'll take the derivative with respect to phi, because it's the variable. It's actually the only variable we have. But again, it is by the problem statement is the variable we would like to minimize. Sometimes this is not clear, but here it is. And then I just differentiate this expression. Now this is a constant, so I can only focus, so I need to focus on the derivative of this thing. And the derivative of the cosine function is the sine function. As for the other derivatives, so the derivative of this function, it's a constant function. So in the derivative, this is equal to 0. And now for this one, in the derivative of the cosine function is negative of the sine function. And since these are constants, I can just look at the derivative of 1 over cosine. And I think that's going to be tangent over cosine. It would look like this. You can check this yourself, of course. But from my side, I will not. What I will do instead is I'll just write the answers down. So I get a sign here, I get a sign there, well, negative sign. And this is 0, so I don't need to write it. And that is the same thing, but with the tangent on top. Now, as with any optimization problem, you take the derivative of the function and you set it to be equal to 0. And then you get some results. So this will give us the same expression, but so if you add the negative counterpart of this thing, it will be this minus that. You can of course check that if you add these two terms, you'll get 0. Yeah. So this is not horrible. We see that we have G VL divided by 2 and just cancel them out. And now notice now that in the problem statement, I was also given a certain equation, which is true. And it is given as follows. So the equation said that in the equilibrium position, H is equal to 3/4 of L times cosine of phi. So that is something that is that was granted to us. Didn't work for it, we were just given this And so in this case, we have rho W sine of phi is equal to rho naught of sine of phi, but then you take away 1 over L squared, and then you have cosine of phi, sorry. And here I want to make a quick substitution. So instead of the tangent function, I'll write sine divided by cosine. I hope that's okay. It should be. But let's not forget to multiply by h squared. And I hope you don't mind if I remove h squared and I replace this term instead. I think you won't mind, and I think you will really enjoy this part. So I square this whole thing. This is h. I square h. I get 9 over 16. I get L squared. And I get cosine squared of phi. And that's amazing, because cosine squared cancels with cosine and cosine. L squared cancels with L squared. And then you have the following. So density of the wood, it would be times the sine of phi would be equal to density of water times sine of phi minus 9 over 16 sine of phi. Notice that these are the only two terms that are left, so that's why we have this statement. And of course, this is just sine phi, but I mean, this has a coefficient of 1, this has a coefficient of minus 9 over 16, so the result really is 7 over 16. But then this is the most favorite part, because it means I can conclude this problem with the fact that density of the wooden part would be 7 over 16th of the density of water. So it's one of these problems with where everything just cancels out very nicely. And this is something that's always good to see. So this should be the answer for the exercise.